Yeah, that's totally fine. Yeah, we can definitely do more of the circular function stuff, especially since you joined like halfway through. We were having a
Yeah.
look at it, so we could probably even just go straight to the very beginning on that.
Um, does that class start earlier?
Does that class start earlier? The circular function stuff?
Yeah.
Yeah, because
'Cause-
we go through a set curriculum with the group class stuff, so you'll
yeah.
basically join in the middle of that curriculum bit, which is why it was a bit different. Basically, you had to jump in without the sort of fundamentals, which I could imagine being a bit tough.
Yeah, it was.
But
So
yeah,
did
go ahead.
that start earlier, or did I join the class late, or have you done revision for that before?
No, so you didn't join late. It's just that classes previous to when you were joined, right? So the classes still start at the same time every day. It's just that like a couple of weeks ago we were looking at it, and week to week we were building up. I think it was 2 lessons on some fundamentals there. So yeah, basically there was um, a lack of the fundamentals for it, but that's fine.
Okay.
So
Yeah.
let's even just go straight to the beginning of circular functions. Make sure that we can get those all nice and good. So okay, let's have a look. Let me pull up some notes for circular functions specifically. Starting with the unit circle. So basically, circular functions is an addition onto your trigonometry related stuff, is what you can basically think of it as. You know, you've got your SOHCAHTOA with the sine, cos, and tan, and how they each have their own equations, basically. What you started to do in circular functions is start to imagine it as its own function, right? Where theta, the angle inside of your trig ratio, is a variable in this case. And you can represent that on a unit circle being a circle with a radius of 1, centered on some origin. And so what turns out to be the case is if you were to draw a line directly from the origin to any point around the circle, you can actually create some sort of triangle based off of that, right? It's going to have some vertical component to how high the line was raised and how far along it ran for. So you get both a vertical and a horizontal component, both of which would make up the x and y coordinate on that unit circle. The reason why x gets cos and y gets sine is because of those trig ratios of SOHCAHTOA, right? Sine being the opposite over hypotenuse. If you think about the hypotenuse as being the length of the line from the origin to the outside of the circle, well, when it's a unit circle, it's always going to be a length of 1, right? The radius, you could think of it as. So both of these now have denominators of 1, which basically simplifies the sine and cos down to opposite and adjacent. And so if you look at where the angle is, the opposite would therefore be this side, which is why it's given by sine, and the adjacent would be this side, which is why it's going to be given by cos. So basically taking these trig ratios from something to being purely just trig ratios into now how they can be used to determine xy coordinates on an axis, effectively, around the unit circle. So that's why you would have seen we were going through like sine and cos being x and y. Okay. From there are certain exact values that you'll have to memorize along the unit circle. We broke it into the quadrant boundaries where it should make sense now that all of these are going to be some form of 0 and 1 because of the radius being 1. As far out to the right or left, up or down, you can only ever go a maximum distance of 1. And so you would get this initial table of values there that are related to the coordinates that exist on the unit circle, as well as the relevant angles in there. For anyone who wasn't here for the discussion on radians, basically you'll start seeing these values of pi as angles around the unit circle. Where that came from specifically was if you think about the circumference of a circle as 2 pi times r, when you have a unit circle, r is 1. So the circumference of this circle is 2 pi, and the reason why these are labeled in terms of pi is because you can kind of think of it as them being labeled as the percentage around the circumference, the unit circle that you're headed towards. Quick question, can we look at a bit of 3-4 calc today? Probably. Can we look at a bit of Let me know if there's anything specific from calc, and we can touch on that for sure. For now, we're going to do a bit of a review on some of the fundamentals on circular functions, do a bit of those questions, at least probably the solving and the evaluating, and then from there we could probably move on to calc. Just let me know specifically what in calc. Those are the boundaries. The reality is you'll actually have to have this full unit circle here. For the purposes of this, you can just use a reference, right? So you can just use this as a reference. Basically, every single angle has some relevant coordinate attached to it. We go over ways to memorize things, but this being a review, probably just stick with using this photo that I'll put in the chat as for, basically, if I were to say, like, do sine of pi over 4, for instance, you look at the pi over 4 spot, and since sine is the y, you would give that. You're essentially using this as a reference. For more info on like how to memorize this sort of stuff, there's going to be the past recordings if you wanted to have a look at that, or our resources as well in the individual lessons that are in there. There's one for tan as well, so again, just using that as a reference for any tan values that come up. Tan isn't directly associated with any x or y, which is why it has to sort of have its own unit circle there. And so yeah, we just, we have their own values that are associated there. That should be about it for fundamentals there. Let's start having a look at how we can now use it in a bit more detail. Cool. So why do we care about having a unit circle? It allows us to solve things like this. So these are the kinds of questions where you have the circular function and the angle, but you don't know, or at least you have to figure out what it equals. Under these circumstances, because you have the angle, first thing you do is you look up the angle on your unit circle. Then, depending on if it's sine or cos, you'll give the x or y. Sine is always the y, cos is always the x. So in this case, because it's sine of 3 pi over 2, we look in this spot, and sine means we take that value, -1. Cool so far? Yeah, any questions at all? Okay. Now, sometimes in the book you'll get angles that are larger than 1 revolution. One of the ways the unit circle works is, yes, it has 1 full revolution, which will end at 2 pi. And in this example, I'm just sort of showing you how you can count around in terms of pi over 3s. Technically, you can also go through even more revolutions. So when you go in your counterclockwise motion, ending at 2 pi or 6 pi over 3, the next one therefore would be 7 pi over 3, 8 pi over 3. You continue to count over and over again. So when you get an angle that is greater than 2 pi, greater than 1 revolution, there's a few ways you can handle it. If it's sufficiently small, like this, then yeah, just continue to count over and over again until you hit the relevant spot. So in this case, we can see pi over 3, the spot of pi over 3 is exactly the same as the spot on 7 pi over 3. So it's functionally identical to just looking at that coordinate, and because it was cos, we take the x value that's relevant there. If it is too big, you don't want to be counting that many times, what you can do is you can make use of some symmetries of the unit circle. So in fact, we could probably go back here for a bit. What you'll begin to notice is actually that's not a great example. As you keep counting around the unit circle, in terms of semicircles, let's say, you'll have 0 over here, you'll have pi over here, then that'll be 2 pi, then 3 pi, then 4 pi, 5 pi, 6 pi. What you'll find is that all the odds are over here and all the evens are over here. And we can make use of that. The way we're going to make use of it is to take that value, split it up into a mixed fraction, I think they call it. Is it a proper fraction? I don't really remember the term. Point is you separate it into the whole number and the remainder. Right? So 6 fits into 55 9 times with 1 remainder. And obviously we have pi's there just because it's in terms of pi. This whole number that you have, the integer value of pi, you look at whether it's odd or even. In this case it's odd, so we start on the left-hand side. And all we do from there is count whatever's left over. So it greatly minimizes the amount of times you have to count around the unit circle. And lastly is the negatives of angles. So the easy way to handle negatives, well, we'll take a step back first. What negatives are is going backwards around the unit circle. So we're used to going in a counterclockwise motion. Negatives are the opposite, right? So you go in this direction instead. And it is a direct mirror of the original unit circle, just with the angles in the opposite direction. That's what it is. As far as how you would more easily solve it, I do it in 2 steps. First is just ignore the negative on the value and just treat it as positive. So in this case, positive 7 pi over 6, and then flip vertically. Because each of these quadrants are going to have some pi over 6 type denominator. All you're going to do is, wherever you end up, flip vertically from there. So in this case, we started at 7 pi over 6. We're going to flip that up. This spot is equivalent to negative 7 pi over 6, which we'll see, if you remember that being in the top left quadrant, exact same spot over here, top left. Negative 7 pi over 6 is the same thing as the 5 pi over 6 spot there. So whether it's positive or negative, you're more or less treating them the same way with the same sort of ideas. You just do one additional thing for negatives. So that's a bit about how you would then start using the unit circle for these kinds of questions anyway. Is there anything to clarify further about that? Cool. The other kind of question is where you are told the circular function itself. You're not told the angle, but you are told what it equals to. So cos x, the x angle is unknown, but we know that cos is equal to root 2 on 2. These kinds of questions will also come with a domain associated with it as well. So that's there because what we talked about earlier with being able to go around the unit circle multiple times. So we need to have a restriction on the domain, because if we don't, there are going to be infinite number of ways you could go around the unit circle. So we need to have some sort of restriction there to limit the number of possible solutions. So up until now, we have been looking at our unit circle, finding the value or the angle on it, and then reporting whatever the, maybe we'll use this one instead, looking at the angle and then reporting whatever value made sense. Now we're going to do the opposite. So we're going to start by looking at the values first and then look for what angles were associated with that. It's just the direct opposite there. So in this case, cos being equal to root 2 on 2, it's cos, so we want an x coordinate, and we want to find where are our x coordinates equal to root 2 on 2. Going to be here and here. Those are in the x coordinate spot, and they are equal to root 2 on 2. Now all we do is report the angle, right? The angle here was pi over 4, so that's going to be one of our solutions. The angle here is 7 pi over 4, so that's going to be the other one of our solutions. So we literally just write that out exactly as written there. That's the most fundamental kind of example. You just got circular function equals value over a single cycle, 0 to 2 pi. Anything to clarify about that example? Cool. Sometimes you'll have to do a bit of rearranging, right? Like this one isn't super easy to see exactly what's going on there. The ultimate goal is to essentially get the circular function on one side and then one of the exact values that exist on the unit circle on the other. So like, yes, there is 0 on the unit circle technically, but because we don't have the circular function on its own like this, we can't really just look directly onto it to get that. We need to get the circular function on its own first. Then from here, it's the same as before. In this case, it's sine equals root 3 over 2. So we do the y values equals root 3 on 2. That's there and there. And yeah, once again, just reporting the angles. Yeah, let's do this. So you will also come across times where you'll have different domains, right? They're not all just going to be within one cycle. In fact, they might even go in the backwards direction as well, the negative direction. We're still going to handle it more or less the same way, where you're looking for, in this case, y values equaling 0, which is going to be here and here. Those are your y values equaling 0. But we're now going to do it in essentially two parts. This is if you have a negative domain or a split between negative and positive. First, you would split it down the middle. So let's say we start from 0 to pi. Well, if you think about that in terms of the angles, 0 to pi is just going to be the first semicircle there. So we just go through and look only within this semicircle. How many times does the y value go to 0? Or where specifically does it go to 0? That's going to be at this spot here, the angle of 0, and this spot here, the angle of pi. Both of those are valid. Then, once you're happy with the set of solutions you have, you then go in the backwards direction, 0 to negative pi. Reminder that negatives means you're going around in a clockwise motion, so it's going to be the bottom semicircle there, where this spot here would be now considered negative pi. And once again, within this bottom semicircle, where does it go to 0? Well, it goes to 0 again at the angle 0, but we already have that one, so we don't need to rewrite it. But we do need to now rewrite this one here, which is now negative pi, because you're going in the backwards direction. So in total, you've got plus minus pi as well as the x equals 0 as a set of solutions. Any questions about that so far? I don't think there'll be too many more examples to have a look at from here. We'll do a bit of practice, and then maybe when we hit 6, we'll go on to calculus. So if you do have anything you want us to look for on calculus, let me know. Because this example, sort of whatever, that's a bit too complicated. Well, not too complicated, but more complicated than you need for like your real exam. And these, yeah, these just don't really show up in the book. They do show up in SACS though, but we'll look at that maybe after we've done a few practices. So let's give this a shot. Yeah. Let's treat the first one with 0 to 2 pi. We'll just ignore this one says negative pi to 2 pi. So let me start getting this written out on the handwritten notes. So we just got sine equals a half. Sine x equals half for 0 to 2 pi. Cool. So this is the second set of examples we were looking at, where the angle is a thing that's unknown, but we do know the value. So there is a photo of the unit circle in the chat, because this is a sine one. You would want to look at the top unit circle, because that'll contain your x and y values. Alternatively, you can look at the screen share as well, if you'd rather look at the unit circle on there. Well, actually, maybe I'll do... Is this going to be a better example? Not really, it's going to be too spread out. So I'll just get the unit circle up here. Anyone want to take a stab at how we start solving this? Yeah, maybe we'll have the procedure up instead. Yeah, on the screen share, I'll have a similar example that you can copy down, just sort of looking at the steps that are relevant. Step 1, we just want to make sure that the equation is what we need it to be, right? Circular function on one side, exact value on the other. That's already been achieved. So step 1's cool. Step 2, we're not going to look at today. That's for more complicated things. Step 3, so we're now going to look on the unit circle for every spot where sine equals a half. So it's sine, which means we have to look at a specific coordinate. I'll make it an easy question. Does sine give us the x coordinates or the y coordinates on the unit circle?
The Y.
The y, yeah, there we go. Cool. So yeah, basically that means we're now looking for where are all the spots where the y coordinate is equal to a half. That's what this question is now asking. And you would give the angles. So the things on the inside of the unit circle is the solution here. And because we're doing 0 to 2 pi, it's just going to be one revolution around there. So, pro tip, there's usually two solutions in any given cycle of the unit circle. So it's a good benchmark to look for two. There are some circumstances where there's only one, but only a few circumstances like that, specifically on the quadrant boundaries, right, where the coordinates like 0 and 1s, those will typically only have one solution to them. Anything on the inside, usually two. Let's see if we can spot them. Got the unit circle on the screen share if you want to copy off that, or there's the photo of it as well.
Sine of x is half when at like 5 or 6.
Yep, 5 or 6 is one of them. So if anyone's following along on the screen share, that'll be highlighted there. Got the y coordinate being equal to a half at that spot. Yep. What else have we got? There's usually two solutions.
5 pi over 6.
5 pi over 6 as well. So what you'll start to notice as you do a lot more of these is the location of these solutions. If you're looking for y, they are always horizontally attached to each other. Like the solutions are horizontally opposed from each other, because that's where you have a constant y value, right? If you were to draw the graph of y equals some constant, it's a horizontal line at that constant. So when you, same thing applies here, right? When you're looking for y equals a half, the other solution is going to be horizontally opposed directly there. So yeah, 5 pi on 6 will be the other one. Similar idea for cos, right? Cos being the x values. Well, any given x-related stuff is going to be vertically opposed from each other. So for instance, the example we had before of the cos being root 2 on 2, we can see they're vertically opposed to each other. But otherwise, yeah, that's just a basic example of the circular function solving related stuff. So you want to look for whether it's sine or cos, will depend on whether you look for y or x. What the value is the value you're looking for on the coordinate, and then you just label the things accordingly there. I think those are the fundamentals for anyone that was joining later on in those classes. Everything else should now make a lot more sense if you go back and look at those recordings or do any other practice stuff that we have here. Cool. Maybe we'll do one on the evaluating. It's usually the easier kind of example though, so we should get that done relatively quickly. Maybe we'll practice a negative one actually, to make it a bit tougher. Can I spot one, or do I have to make one up? Yeah, I guess I've got to make one up. That's fine. So let's do tan. Why not? Tan of negative 3 pi on 4. So this is the first set of examples we had where we know the angle and the circular function, but we don't know, or at least have to find, what it ends up equaling. The challenge here being that we now have a negative angle, so we've got to handle it a little bit differently. I'll have the procedure up on the screen share. It is looking at the xy, the sine cos unit circle. For tan, we're going to be looking at the tan one. So if you want to use the photo, I'll put it in the chat as reference. That's cool as well. So negative 3 pi on 4. First thing we're going to do is figure out just like where that is on the unit circle, full stop. How could we figure that out?
we can take the base value first, the first quadrant value first, and then we can start with the first quadrant value and then go from there.
So first quadrant would mean this top
Oh,
right. Did you mean to start there, or did you mean something else? Because you can.
yeah, I meant to start there.
Yeah, cool. So how do you do it from here
And
then?
well, we can go pi by 4 units back until we reach 3 pi by 4, which would be in the second quadrant in this case.
Oh yeah. So are you counting backwards or forwards? So this way.
Backwards.
So from 0, you're counting pi over 4s.
Negative pi over 4.
From negative pi over 4, you're counting pi over 4s.
Yeah.
So negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4. Like that?
Yeah.
Yeah, that's totally fine. It's a relatively shallow angle, and so you can very easily count that out, no worries. When you start having bigger stuff, that can be a bit more complicated. So what I've outlined here is it can be easier to just pretend, hey, first pretend there's no negative on it. So in this case, you'd be looking directly at the 3 pi over 4 spot, and then from there flip down. So that way you're leveraging use of the positive that you already are probably going to be more familiar with. But again, there's multiple ways of doing this. It's whatever you want to, however you want to go about it. So yeah, that's going to put us in that spot on the unit circle. I'll just pull over to the tan relevant thing there. So it's going to be here. Tan value, fairly trivial at this point. It's just 1, right? You just report the value that's at that spot. So in this case, we have a solution of tan negative 3 pi over 4 is equal to 1. That's pretty much it there. Cool. Okay, that'll wrap up some circular functions fundamentals. So hopefully that explains things in a bit more detail there. You wanted to have a look at some calc stuff. Was it anything in particular? Nothing? Okay, sure.
In calculus, when you're asked
Hmm.
to comment on a graph that's strictly increasing or decreasing, should the brackets be inclusive or non-inclusive?
Yeah, that's a great question. And I keep having to look up my old, because I looked into it a couple of times and I wrote it down. Whether it's strictly increasing or decreasing, do you include? So it comes back to the definition of what strictly increasing or strictly decreasing means. Let me just revise that real quick. I'm pretty sure it is inclusive, but I've just got to double check that to make sure. Let's go to strictly increasing. Okay, so for strictly increasing, the y values, so, okay, f of a greater than f of b, where a is greater than b. So let's get a picture going on. So we have a is greater than b, so along our x-axis, a is ahead of b, and f of a has to be greater than f of b. Okay, so looking from left to right, as long as the y values are bigger, always, then the graph is strictly increasing. Now, whether this is inclusive or exclusive is going to depend on what was before it. It's going to depend on what was before it, even though there's a restricted domain. I might just have to look this one up again. Do we have examples of domain over which it is strictly increasing or not? State whether it is. Is it strictly increasing on the stated interval? Okay, well this is kind of it. Because you've got, yeah, this should be valid for more than just 0 to infinity. Let's see if we can infer from here. So 0 to infinity, is it strictly increasing? What's this question? 7b, 21c. Let me look that one up. Seven B 21C does say yes. So my assumption would be that, yeah, you would have your closed brackets on that. We'll double check the graph itself just to make sure that everything else is on par. So for this graph in particular, e to the x plus e to the minus x over 2. E to the x plus e to the minus x over 2. So it doesn't look behind, because if it did, then it wouldn't work. So the domain that you have is treated as the exact starting point on there. Because if it did look behind, then this would be a false, right? Because the value before it is bigger, not the value in front. So over the domain 0 infinity, inclusive, yes, this is considered strictly increasing. So yeah, my initial remembering of it was right, that you do have inclusive brackets there. Because the function doesn't exist anywhere behind that or in front of that. Well, it does in front of it if it's, you get what I mean. It doesn't exist anywhere behind if it's cut off at 0. That explain that enough? The take home
Yes,
is,
thank
yeah,
you.
the take home is use inclusive. Cool, okay. Because yeah, that shows up in calculus, because some of the ways people will try to solve this is by looking for gradients, right? For strictly increasing would imply that the gradient is always some positive number, because if it was ever gradient 0, yeah, that's where it gets a bit weird. So what I wanted to highlight there is using calculus, using derivatives and gradients to try and figure that out is a bit wonky, because this is a stationary point if we look at the graph that we just created. So gradient 0 can be involved in strictly increasing so long as it's only a momentary stationary point. If it ever goes flat longer than a single x value, then there's an issue. So typically the way you want to solve these is with a non-calculus approach, looking at the actual graph itself. And yeah, that's pretty much the only way you'd be able to, or the best way to go about it. Because, you know, sometimes you'll go, is gradient positive the entire way? And if it is, then by all means, yeah, it's definitely going to be strictly increasing. But yeah, strictly increasing does allow little momentary stationary points, whereas just regular increasing would allow longer flat points as well. So if it was just increasing, then you're allowed to have flatter points for longer. Okay. Was there anything else derivatives related we wanted to revise specifically? Because if not, I'll just sort of go back to like just fundamentals. What's derivative and how are we going to use them? Cool. Okay. Let me pull up some. Should we do diff by first principles? Probably no, only to talk about it. Okay. So what actually is the derivative? I mentioned this a bunch of times for anyone who hasn't done calculus related stuff. Basically, it's this process of trying to find the gradient at a particular point on a graph. For things like linear, that's really easy. The gradient of the graph is always constant. It's constantly rising or it's constantly falling. For graphs like a quadratic, you can see it's got curves to it. And so the gradient, the slope of the graph, is increasing over time here or decreasing over time on this side. So it's hard to figure out, hey, what is the gradient at any given point on this graph? One of the things people started to do to approach this was to approximate it and to say, hey, here's 2 points that are close enough together. We can draw a straight line between them and figure out the gradient of that straight line because it is a straight line. Nice and easy, just rise over run. And so basically the idea is, what if we took 2 points that are really, really close together? So instead of doing 0 to 2, we could do 0 to 1, or 0 to 0.5, 0 to 0.25. You can see that as you choose points that are closer and closer together, the approximation that you get for the gradient is going to be a lot better. To highlight that with a bit of a picture, I'll pull up this. Right, like you can imagine zooming in on that and the points being so close together that basically when you draw the straight line there, they are effectively the same gradient at that spot, or they're very close to being the same gradient. And that's what differentiation by first principles means. It's like the first introductory into differentiation. You just take two values that are really close together. You use these things called limits, which a lot of schools just sort of barely touch on, which is fair. It doesn't really show up much in the exam anyway. In fact, I think maybe it only ever showed up once in a multi-choice ever, and there's literally a thing on your calculator that can just do it for you. Like, you can just type in exactly limit and then get it sorted. So you don't really need to know the ins and outs of this specifically for exam-related stuff. More so, this was just like an intro to what differentiation actually is. There's a big nasty equation that can actually be simplified with some rules. Some generic rules can be applied to different types of functions, which we'll have a look at next. Rules for differentiation. Okay, so this is what you get on your actual exam. You get this on your formula sheet. It is a table of derivatives. On the left-hand side is the type of function that you have. So you'll see we've got our power functions, some exponentials, logarithms, and the trig stuff that we were just looking at recently. That's on the left-hand side. On the right-hand side is the rule for finding the derivative of that particular function. The derivative is related to gradient. The derivative specifically is its own separate function that tells you the gradient of the original function for all possible values of x. So we'll have a look at that quadratic example again, right? So we knew from the quadratic, it had a lot of different slopes at different points. Before, we were kind of just plugging in points and getting them manually ourselves. By using differentiation, we can create a separate function that tells us the gradient at any point on the original quadratic. The way you do that would be, at least in this case, with this rule here. So basically it means anytime you have some x to the power of n, any power at all, that power of n goes out the front as a multiplication, and the power gets reduced by 1. So for the quadratic, we got x squared power 2. That 2 is going to come out the front as a multiplication. 2 minus 1 gets you back to 1. This function, now, you can plug in x values and therefore get the gradient at any point on the quadratic. So I'll pull that other example up again, just so we can have a look at a picture of the quadratic. So let's say I put in x equals 1 into my derivative function. That's going to give me the value of 2. What that means is, at x equals 1 on my original graph, the quadratic, that gradient there is 2. Similar thing if I subbed in x equals 2. I would get 4 as a value, which means that at x equals 2, the gradient specifically here is 4. Don't worry about this line, that's connecting the two. Specifically at this point, the slope of that line would be 4. I'm harping on about that specifically because a lot of people will, I see it all the time, where they've got their derivative function, but they're still trying to shove x and y values into it. This goes from being an xy graph to now a gradient x graph. Gradient is on your y-axis. So when you have points to substitute, sub your points in here. This thing only takes x values and gradient values. That's it. A bit on notation. So you can denote the derivative of any f of x as f dash of x. If the function was instead called like y equals x squared, you might start using things like dy on dx. These all mean the same thing. It does kind of matter though, based on like just a bit of nuances on how you answer your exam questions. Like for instance, if I pull up literally any of the exam ones, it'll tell you what notation to use. So this is y, so you have dy on dx. This is f, so you have f dash. In your final answer, say dy dx equals this. Say f dash equals this. Don't intermingle them. That's not to say you'll get it wrong, but it'll when you're on the board of getting a study score increase, like you're right on the edge of getting that 40, let's be ambitious, they'll give it to someone else because they wrote dy dx as opposed to f dash. Little things like that give you slight edges. Won't change your actual grade, but change your maybe if you're on that edge of getting a new study score. What happens if you have more than a sequence, more than just one function? If you have like a sequence of them, essentially you just handle them individually. So here's 4 sine x, and you got a minus 2 natural log. You do the derivative of this thing first, then the derivative of that thing second. Technically, you can do it in any order you want. The addition or subtraction doesn't really change the order you do things in, but it's just easiest to flow from left to right. We're very used to that. This is the like mathematical way of showing that. So basically, if you have any functions that are added or subtracted together, you do the derivative of each individual one and make sure the sign still separates them properly. Also worth mentioning is if there's any coefficients on those functions, you can take them out of the derivative operator itself. So for instance, 4 sine of x, if we look at that, 4 sine of x technically is not sine x, right? Those are not the same thing. 4 sine x is 4 times sine x. So technically speaking, you shouldn't be able to use this directly and get the answer. Now, getting around that is trivial, because multiplication is distributive. Basically, it means that you can pretend it's not there, do your operation, and then put it through at the end. That's all that's saying, basically. So 4 sine of x, you just treat it as regular sine of x first, do the derivative of that. So once again, we'll look at what that was. Sine equals cos when you derive it. So we replace the sine with cos. So we had sine here, we're replacing it with cos, and we're just bringing that 4 through back at the end. That's all that is. You'll do it enough times to where you won't think about manually taking it out of the front. You'll just kind of do it. I've done the same thing over here. So distributing the 2 outside, derivative of natural log is 1 over x. So that's this one here. Derivative of natural log is 1 over x. So you just replace the left-hand side with the right-hand side. There was still a -2 at the front, so we just make sure that works out the same way. This one was y equals, so we're going to use dy on dx as our notation, rather than f dash. I am highlighting that simply because in my working out, I'll probably be a bit lazy with it and use stuff like y dash and f dash just out of habit. I'll be mindful not to make it as accurate as possible. Any questions on those fundamentals? Just looking at our derivatives table and based on whatever function we have, just replacing it with a different term. At least that's pretty much the entire procedure.
Why is differentiated a form of a natural log of x just 1 by x?
Yeah, why is it? Great question. So it's going to come back to differentiation by first principles. The full differentiation by first principles equation is this limit. I'll just double check. Are you familiar with this yet? I might have to explain this in more detail if you're not familiar with that equation. Okay, I'll assume you're not. So this is the fundamental way of doing the derivative. You've got this delta x term here, which is signifying the gap that you have between the 2 points. We talked about it being like taking 2 points that are really, really close together. We're now going to define that gap as a specific variable, delta x. That's the gap. Then from there, this is essentially just a rise over run. It's y2 take y1 on x2 take x1, where x2 take x1 is the gap delta x. And we're chucking it in a limit because we want to see what happens as that gap gets closer and closer to 0. You can do that for any two functions, the natural log of which is also a function, right? And so what they do is they don't use an actual point, they just do it purely in terms of this x-related stuff. And as it turns out, as you simplify things over and over and over again, you will eventually be able to simplify it down to 1 over x. I don't personally know how to do that properly. I will check to see if they're given a proof for it, although I doubt it. No, they didn't do it. Maybe it's in an appendix. Oh, what I'll do actually is I'll show you an example of a yeah, here you go, they did it here. They did it for an exponential, where they're starting with the proof of the basic, not the basic, the fundamental differentiation, and then they're saying how you can, or showing how you can simplify things down over and over again to something different. They did the same thing for, yeah, they're doing it here as well. And yeah, I guess maybe the natural log one is just so complicated they didn't bother writing it down. But they do definitely show at least a few proofs of those, so you can get the idea of it. Where's the... Yeah, here you go. Here's one for polynomials, right? So you expand out that term, you'll get a bunch of power terms that are descending. A decent amount of them are going to cancel down. There's just a bunch of simplification to get it down to that. They do it generically with some generic polynomial f of x. They don't sub in an actual point. All that to say, if you're curious about why, probably just Google the Wikipedia page on it or something, and you'll see the proof that is similar length of this. Fair enough. Otherwise, yeah, just look at the table.
I've got another question.
Yeah, mate.
In my book it says e to the kx. If I find the derivative of that, it's k times e to the k of x.
Yep.
Why is that?
So that is something we are yet to look at, which is referred to as the chain rule. So I kind of lied a little bit with what you get on the formula sheet. You get a little bit more than what I was showing there. And that's sort of deliberate because I wanted to teach chain rule as its own separate thing, because if you're just looking at this, there's no, like, you're not necessarily knowing you're using a specific rule for it. But what you'll notice is in all of those, like you had k instead of a here, in a lot of these functions, they have another coefficient in there, and you can see in a lot of cases that coefficient is an additional multiplication on your result. So instead of having e to the ax, you now have a e to the ax. Instead of having cos, you now have a cos. As for why that is, we'll have a look at that now. So let me pull up the chain rule. So what I've shown you so far is all of the fundamental functions. Like, this is as simple as the functions get. It's just e to the x, natural log x, sine x. There's no other coefficients anywhere else at all, no other transformation factors in the slightest to consider. As soon as you have anything other than just x in there, you now have to use the chain rule. Did I not pull it up? Oh, it just didn't come up. Nice. There we go. We now have to use the chain rule. So in other words, whenever you have a composite function, right? Some function inside of another function. This is no longer just x, it is x squared. Same thing could be said for if it was 2x in here. The chain rule is such that you basically want to split your composite function up, whatever it is, into the inner and the outer, right? What's g of x, what's f of x? Or more specifically, what's f of g, because you want to eventually then rewrite your function in terms of that substitution that you're going to do. So let's have a look. Basically, we identify it's a chain rule because there is a power on the x, just anything on the x that's not just x. So we take the inside of that function, let it equal to g. All right, g of x is equal to x squared. Then rewrite that original function in terms of that variable that you just substituted. So every time you do this, you should always get back to one of these on the really basic table. There shouldn't be anything else involved in here, otherwise you've done a substitution wrong. Should go right back to the fundamental one. Yes, it's going to say g instead of x, or whatever variable you use, but, you know, get it to its fundamental state. Then, take both of these and find the derivatives of each of them. X squared, we've done that before, that's just 2x, because the power goes down the front and reduces by 1. Natural log of g, well, 1 over g. Right, that was your question earlier. Why is it 1 over g? Natural log turns into 1 over. Then those two derivatives just multiply together. So the actual formula is dy dx equals dg dx times dy dg. This is derivative of y when you write it in terms of g. This is derivative of g when you've written it in terms of x. So that's your dg dx, that's your dy dg. I've also written the dash version as well, if you prefer. But on your formula sheet, you'll get dy dx notation. Yeah, you multiply them together. So 2x times 1 over g is going to give you that. But we've got to get back in terms of x. So we know that g was x squared, so just put the g back as x squared and simplify whatever you get. That was a more complicated example where you've got x squared. What you'll find is that if you do it for any of the other things with just a simple coefficient on there, that's where these come from. Basically, you're using a chain rule, and because you're differentiating the thing that's on the inside, the diff of this is always just a. Right? Ax goes down to a. It's linear. Any diff of linear, because there's a power of 1 there, will just sort of go to 0. Ax goes to a. Ax goes to a as a multiplier on the front. The next natural question is going to be, why doesn't that exist for log? Why does everything else get an ax but not that? But before I address that, is it fair enough why these ones are working the way they are? Can we do an example question for chain rule? Yeah, we can do that. Cool. I'll just make one up. They're not too bad. That should take us, yeah. Let's go sine of 3x plus 2. Got y equals sine of 3x plus 2. First step, why is the chain rule? Well, we don't have just x in that function anymore. It's not as basic as regular old sine x. So step 1 is going to be to split up the relevant functions. So let's try and do that. How are we going to create this split?
We can do it as sine of x and 3x plus 2.
Yep, that's the split. So use whatever variable you want to replace the inside, and then the outside is now going to be written in terms of that variable. Just don't use x again for this, because that would be technically inaccurate and will just cause a bit of confusion. So as long as you use any other variable, any other variable that's not the one you're replacing. Yeah, so we do that split, right? Take the inside in this case, replace it with 3x plus 2, and then, rewriting it as u. That's step 1 done, splitting it up. Steps 2 and 3, what we're doing there.
We can find the derivative of both equations.
Yep, derivative of both, absolutely. For those who aren't quite familiar with them yet, I'll keep those up on the screen share if you want to look at the table. What are the derivatives of these?
So u, the derivative of u is 3x. Sorry, wait, 3, just 3.
Yep, just 3. So constants are just flat values, and so they go to 0. They have gradient 0. And the linear, right, the gradient is always just the value, so 3. Yep, du dx is 3, and dy du is
Cos of x.
cos of x. Yep, that's it. Sine goes to cos on our derivatives table. Cool. We have our two things. What do we do with them?
You can substitute them back in.
So what does that look like?
So cos of 3.
Cos of 3 isn't the full substitution. Remember, it's u that we would replace that with. So it'd be cos of 3x plus 2 if you're subbing it back in. Is that what you meant? Like as in, did you mean substitution, or do you mean to use this 3 over here?
Just the 3, the derived one.
Okay, so what do I write as my next line?
Cos of 3.
Just like that?
Yeah.
Nah, not quite. So 3 is du on dx specifically. So the chain rule states that you want to take these two things and multiply them together. We have dy on dx is equal to du dx multiplied by dy du. There's dy du, there's du dx. So you want to multiply those two things together. The substitution comes in because this is u, not x, and u is over here, right? So we are still using this term of the 3, right? We have 3 cos of u, but because it's u, we're now going to replace it with what u actually is in terms of x, 3x plus 2. Make enough sense how that's working now?
Yeah.
Sick. Yeah, that's chain rule. So graduating from having the fundamental function to now a composite function, essentially. I'll do a quick thing just for fun. We might run slightly over time to answer the initial question that we had before, which was that I suggested, which was why is natural log not having the a in there? Why is that not there? Let's have a look with a chain rule example. So I'll do it just sort of live myself. Y equals natural log of ax, right? Which is going to have some coefficient there. First thing you want to do is split it up. So the inside is going to go to u, and therefore y of u is going to be natural log of u. Just splitting them up. Oh, there's a bit of weird glitchiness there. Then the derivative of this. So derivative of any linear is just the coefficient, so a, and the derivative of natural log, so y dash is 1 over u. Right? Natural log goes to 1 over u. Then finally, these have to multiply together as per the chain rule. So our final dy on dx is going to be a times 1 over u. But u is ax. A over ax, 1 over x. So any coefficient there at all will not matter. It'll just cancel itself out, specifically for the log. Just a fun little thing. I get that question occasionally, which is like, hang on a minute, what if I have an ax in there? What am I going to do? I guess they were in a situation where they had to decide, am I going to put ax here and have it be the only derivative that doesn't have an a in it? Is that more confusing than just not having it entirely? I guess that was a situation they were in when they were creating the table. But at least now you know why that's not there. Cool. All right. That hits time on that one. I'll stick around for a bit if we have any further questions. Otherwise, I'll let you enjoy the rest of your week.
Thank you.
Thank you.
Hi, Chris. I was just wondering, since the links got updated, is it still using like the same links every week?
Yeah, yeah. So it'll be if I ever change them, I'll make a post. I doubt
Yeah.
I'll have to keep doing them every week. That'd be a bit insane. Unless it gets leaked again, of course. Which I mean, I guess it can happen. It happened one time. It could potentially happen again. If that starts being the case, rather than doing that, I'll create a new set. Yes, but if it starts being an issue, I'll make them invite links. So you can literally only join if it's directly attached to your email. I don't really want to do that just in case you guys are using different computers or trying to log in from different spots.
Yeah.
But if we have to, we have to. I'll make sure everyone's in the loop though, if that's the case.
Cool.
Easy.
Yeah. Awesome. Thank you, Chris.
Cool. Thank you. Have a good one.
You too. Bye.
Hey, I've got a probably unrelated question, but you do engineering, right?
Yeah.
Or did?
Yeah, I did it for about 1.5 years, 2 years ish. Yeah.
What field of engineering?
So it was called firmware engineering. The degree
firmware. Cool.
yeah, the degree I specifically did was in RMIT electrical/electronic. It's your 4 years basic honors degree there.
Oh,
Yeah, can recommend. It's good fun. It sounds like you're into the programming related stuff.
yeah.
Yeah, what kind of
I've
stuff are you
been
getting into?
I'm learning C++. I know the basic syntax of C.
Yeah.
And I just want to like play around with my Linux kernel and stuff.
Oh, sure. You run Linux, do you? Yeah. Okay. You're already taking it a step further than me. Then I'm still running Windows. Because yeah, no, I get you.
Yeah.
No, that's sick. Starting early. No, real good.
Yeah.
Yeah. So
Okay,
Yeah.
if you like, what would you recommend if I like computers and stuff, like low levels?
you want to get lower level. Okay. Yeah. So for that sort of thing, firmware is pretty much right up where you'd want to be. I know you mentioned you were keen on like the ASM assembly stuff. Assembly, I would be shocked if anyone, like any real job, is actually doing anything assembly related. That's quite low down. You do it just because you want to get a nice fundamental of how the computers are actually running. So if you are keen on like just the learning side of things, on how how your computer is actually running, what are the fundamental buses and the literal instruction, the bit fields for the actual instructions that go on your CPU, then yeah, getting into assembly, learning firmware engineering related stuff will definitely take you on that path. Do I still have my stuff on it? I don't know how. Yeah, because I could send you, if I have them, my like uni notes, if you're curious about like the assembly related stuff and the and that sort of thing. I just got to remember where it is. But
did you use like any assembly in your job?
no, not on the job.
Okay.
So that's why I was
What about
mentioning,
C or
right?
C++?
So for firmware, for what I was doing specifically, no, they did have a software department that would be considered software specifically. And you'll typically find software will be for your applications, right? Like your Zoom, your any application that you install on a computer. Whereas what I was doing was, I touched on this a bit earlier when we talked about it last time, was there are these devices called FPGAs, which are programmable logic boards or chips. The way it kind of works is you have this grid, this array of potential logic gates, whatever you would, I don't really know the technical term for it, but basically, things that are things that could be really easily soldered, or on the brink of being connected as physical wires. And you can literally
something like a breadboard or?
Kinda, but code is connecting the nodes.
Oh, okay.
It's like that. So it's software or code-driven physical connections on a chip. And that's what I was doing, making dedicated computer architecture for specific things. Because on your computer, right, you got your CPU for general processing stuff, you got your GPU for anything parallel load, big data that you can do in parallel rather than one at a time.
Yeah.
Stuff like that, right? Creating on the fly architectures designed to optimize how fast a task can run for that particular task that you needed. So, you might have some parts dedicated to sequential, some parts dedicated to parallel, and you'd just be doing your best to try and minimize the amount of clock cycles between how long the typical instructions should run. So it's, it's a little bit above ASM. Still start there just because you want to kind of know it's a good foundation. But then get into, so for firmware engineering, you would be using either Verilog as your scripting language, or you'd be using VHDL. I'll type both of those.
I'm not aware of any of them, but
yeah, I'll type both of those
good to
in.
know.
That's so I specifically in uni was doing Verilog. On the job was VHDL. Those are things to look up. The syntax isn't too much different to regular code. The thing you got to get used to is, because what you're doing in that code is defining actual physical pieces of architecture, like you're defining registers and such. So code running sequentially is a thing, yes, but you've got to think about it in terms of clock cycles rather than in terms of like looping through the software. It's a little bit of a different nuance to it. But there's going to be like free lecture stuff, like on MIT OpenCourseWare. Like there are universities that literally post their lectures on these sorts of things for free.
Okay.
So that can give you a nice. It won't be the same as RMIT or whatever, of course.
Do you know about CS50? I've watched a few episodes of that.
Don't know it by name. What's that cover?
It's the I think Oxford's computer science introduction course.
Yeah. CompSci, I don't know if CompSci will ever go down to assembly level or like those fundamentals, because it's not super necessary for the job. You'll typically be using libraries and like up other people's code, basically. But if it's got it, it's got it. I just know that in my experience, it's definitely covered in your electronics / firmware related things.
Okay.
But yeah, you have a few leads to go off of there. All you can put. Yeah, I'll dig through and see if I can find some specific stuff to follow up on, like some of the freer, I guess, like places that post YouTube related stuff. I guess
Yeah.
I'll see if I can find stuff that was as relevant as what I was doing. Because you said you wanted to look at the lower level stuff, yeah?
Yeah.
Yeah, sick. But yeah, I mean, look, anything's going to be better than nothing, of course, if you're currently studying.
Currently I'm kind of interested in graphics development.
Graphics development.
That's a whole different field, of
It
course.
is, yeah. But no, I mean, so yeah, there you go. Like graphics is usually like a parallel load, so you might use your GPUs, but no, you're not going to be writing you're not going to be defining registers and such. It'll be obviously using libraries and other things to help out, and using the specific IDE, or I guess the actually what is graphics going to, you're going to have an IDE obviously, but you might build it in like a platform.
Yeah. There's a difference between firmware and kernel, right?
Yeah, kernel is, if I'm remembering correctly, like a very base operating system on your hardware. It's what's it close?
Like its definition is that it's a layer between the hardware and software.
Yeah, so it's like the very basic, it's like a really basic operating system connecting the two. Firmware, what I'm specifically defining is, what I'm talking about is literally programming the hardware to be a different physical device. So like turning your CPU into your GPU, kernel's not going to do that.
Yeah.
Right? It's just going to talk between the two.
Yeah.
But yeah, like look it up, right? Firmware, ASM, or specifically FPGAs, if you want to talk about the specific thing. FPGA. That'll be, if you suss out specifically FPGAs, you'll know exactly what I was working with.
Okay.
Cool. And yeah, keep me posted if you're coming across any cool things, or if you want more guidance on that related stuff.
Yep.
More than happy to keep sending you in different directions. Well, the directions you want to go in anyway.
Yeah. Okay.
Easy. Well, thanks.
Thanks.
Appreciate it.
Have a good day then.
You too. Take care.